Hey everyone, welcome to this explainer. Today we're stepping up to the whiteboard, and we're going to look way past the surface of the internet's architecture. We are breaking down the distributed systems that power our daily digital lives.
I mean, think about your daily life for a second. Have you ever wondered how giants like Google or Netflix literally never seem to go offline? You type in a search or hit play on a movie and boom, it just works, instantly, seamlessly. It feels like you're interacting with one giant, indestructible, perfect computer. But as we're about to see, that flawless experience is actually a brilliant, carefully orchestrated magic trick. So here's our roadmap for today. We're going to cover the illusion of one system, the anatomy of autonomous nodes, the magic of transparency, middleware and overlay networks, the cost of partial failures, and finally, real-world routing and trade-offs. Let's get right into it. Section 1. The illusion of one system. Why distributed systems? All right, to really understand this architecture, we have to ask why it was built in the first place. Well, distributed systems are the vital foundation for things you use every single day. Cloud storage, IoT devices, global mobile networks. By linking up multiple machines, they allow for massive resource sharing. Plus, they give us the insane scalability and fault tolerance needed to power modern apps like those Google and Netflix services we just mentioned. They drive global collaboration on a scale that one single machine simply couldn't handle.
Moving on to Section 2. Anatomy of autonomous nodes. Independent nodes.
So here's the core paradox of the whole thing. A distributed system is really just a collection of completely autonomous nodes collaborating to look like one single coherent system to you and me. The big catch? There's absolutely no shared memory, there is no global clock, every single node is doing its own independent thing, yet they somehow have to coordinate perfectly to give us what we want.
To really wrap your head around this autonomy, remember that each node is totally independent. It's got its own local clock, its own memory. Imagine a global team trying to pull off a highly sensitive project together, but no one's allowed to look at the same watch, and there's no shared filing cabinet. Sounds like a nightmare, right? This lack of a global time reference means getting these machines to sync up is incredibly non-trivial. So how do engineers actually hide all that chaos from us? Which brings us to Section 3, the magic of transparency, hiding the complexity. Now, distribution transparency is kind of the holy grail for a seamless user experience. The system brilliantly hides all the messy details. It hides uniform access methods. It completely hides the physical location of the servers. I mean, you have no idea if your data is sitting in New York or Tokyo, right? It hides the fact that your data is replicated all over the place, and it hides all the other simultaneous users, so it feels like you've got the app all to yourself. It even tries to hide its own failure recovery mechanisms when things blow up behind the scenes. But how do these totally different machines actually talk to each other to pull this off? Section 4. Middleware and overlay networks. Connecting the nodes.
Okay, so the actual technological glue holding this all together is called middleware. It literally sits right between the operating system and the applications themselves. It provides common services like remote procedure calls, or RPC, and messaging. Basically, it acts as a universal translator, masking all that network heterogeneity and allowing for some incredible portability across completely different operating systems. It is absolutely the unsung hero of the distributed world.
Now, on top of those physical wires and middleware, we build logical highways called overlay networks. This is how nodes connect to their neighbors. And there are two main flavors here. First, you've got structured overlay networks. These use super precise, predictable shapes like rings or trees. Then, on the flip side, you have unstructured overlay networks, which rely on totally random links. Actually, that is exactly how peer-to-peer systems operate. Both of them are just building a logical web over the physical wires.
Section 5. The cost of partial failures when things go wrong.
We've been talking a lot about this illusion of perfection, but here is the harsh reality. In a truly distributed system, partial failures are basically guaranteed. Some nodes are going to crash and burn entirely, while others just keep humming along like nothing happened. And trying to detect those partial failures, it is an absolute engineering nightmare. Because we don't have that global clock we talked about, how do you even know if a node is actually dead or if it's just running super slow? A system's design absolutely must be built to tolerate these partial failures, rather than just crossing our fingers and hoping they don't happen.
And because of those inevitable failures, engineers have to make some really tough transparency trade-offs. Trying to achieve 100% full transparency is just way too costly. Plus, you literally cannot cheat physics. Network latency is always going to be a factor. Sometimes, trying to mask every single failure actually makes the system perform worse. In some cases, like with location-based services, exposing the distribution is the much better choice. You want your map app to know you're in Chicago, not pretend location doesn't exist.
Section 6. Real-world routing and trade-offs. Balancing trade-offs.
Let's bring this down to reality for a second. Engineers are playing a high-stakes balancing act every single day. They are constantly prioritizing between keeping the system available and keeping network latency low. Imagine a massive traffic spike, an event known as a thundering herd. Suddenly, intelligent traffic steering has to kick in. Do you send traffic to a faraway server just to keep the site online, even though it's going to be slow? Or do you risk totally overloading the fast local server? It is a constant, real-time negotiation to keep the service alive. To actually make those split-second routing decisions across the globe, the physical internet is chopped up into distinct administrative domains. We identify each one using an ASN, or Autonomous System Number. Think of an ASN as basically a zip code for the backbone of the internet. It's exactly what allows routers to successfully hand off traffic between entirely different network owners.
Let's actually track this step by step. Step 1. A data packet leaves your phone or laptop. Step 2. That packet crosses the first mile and hits your internet service provider's router, entering your local autonomous system. From there, it dives headfirst into deep DNS routing, pinballing through a crazy web of different ASNs until it finally hits its target server. And all of that underlying madness, it's happening in literal milliseconds.
This really brings us to a perfect summary of everything we've looked at today. The network is the computer. Whether we're talking about sharing resources through cloud storage, streaming on peer-to-peer networks, or using content delivery networks to speed up websites, the individual machines almost don't matter anymore. The collective, coordinated power of the whole network itself is the computer. It perfectly sums up the magic trick we just decoded.
So, I want to leave you with a thought. The next time you plop down on the couch, open up Netflix, and start streaming a movie in 4K, are you just going to see a single screen? Or are you going to picture the invisible army of autonomous nodes, the layered middleware, the overlay networks, and that relentless behind-the-scenes battle against partial failures? It's an incredibly complex digital world out there, but by understanding distributed systems, you now know exactly how the magic happens. Thanks for hanging out with me for this explainer. Keep asking questions and keep learning.